I'll be talking about the importance of student-led design in my presentation, but first I'd like to tell you a little bit about myself and how I came to this conclusion. So in May of 2013, I graduated from the University of Illinois with my bachelor's in mechanical engineering. I'm currently in the master's program at the University of Illinois, and I'm also working as a student researcher at the Army Corps of Engineers and as a graduate research assistant at the University of Illinois itself. The last 2 years, though, I was the president and co-founder of the Illini Eco Concept team. As a part of this team that I truly came to understand why student-led design is important and why it should be encouraged in the curriculum. So the Illini Eco Concept team was started in the fall of 2011 by a couple of car guys, like Adam was mentioning, in the hopes that we could design a vehicle that was actually practical and we could apply what we knew and loved in a practical circumstances. We were fortunate enough to find the Shell Ecomarathon competition, which allows students from around the nation and around the world, in fact, to build their own vehicle. So, in the fall of 2011, we began building a vehicle for the Shell Ecomarathon competition. The Shell Ecomarathon competition is not a new competition. It was started in the 1930s by a couple of Shell scientists in the United States as a means to explore efficient vehicle technologies. They actually wanted to just compete amongst themselves to see how can we build a very fuel-efficient vehicle given the technology that we have today. Since then, the competition has changed format and actually left the United States for a while, went to Europe, and has come back, and has now expanded into Asia as well. But the overall mission has stayed the same, to develop an exceedingly fuel-efficient vehicle given the technology that we have and pushing technological boundaries in the process. So we found this as a great opportunity to take what we knew and loved and apply it to a competition where we could learn more about the automotive industry and actually participate in the future of the automotive industry. We chose to compete in one of the divisions of the Ecomarathon competition. Traditionally, it's divided into the prototype division and the urban concept. While the prototype vehicles, as you can see above, are intended to be exceedingly fuel efficient. I think the record is more than 5,000 miles per gallon right now in terms of prototype vehicles. We chose to focus on the urban concept vehicles. While these are also exceedingly efficient, they're intended to be more practical. They need to incorporate elements of real vehicles such as turn signals, headlights, taillights, all-weather driving, and they need to work in an urban environment. We felt that this was the best way to actually develop a realistic vehicle that you and I could drive on city streets in downtown Chicago if we wanted to. While the Ecomarathon competition had its own requirements, we wanted to push our goals a step further. We didn't want to just build a vehicle that looked like a real car for all intents and purposes, but in reality couldn't be used in a real-world environment. Our vehicle needed to be able to travel at least 30 miles per hour. It needed to be exceedingly efficient. We set a goal of 100 miles per gallon for our vehicle, but it needed to be comfortable for the driver as well, and his passenger. And it needed to do all this while staying within the rules of the Ecomarathon competition. So we had certainly set a challenging task for ourselves, but it's been a great process in trying to figure out how we can do that. So, given this requirement, we began to design our vehicle in 2011 for the 2012 Ecomarathon competition. Now, a vehicle requires numerous systems to operate properly, and for those of you who were here for Daniel Kim's presentation, you know how much work and dedication it takes to develop a fully fledged vehicle. So here, I'll only elaborate on 3 of the systems that we were working on. But these 3 systems highlight the engineering skills and the design challenges that we faced along the way. The first is the chassis of the vehicle. This can be seen as the backbone or skeleton on which everything else sits. It's therefore a crucial element in any vehicle design, and we attempted to produce the vehicle chassis in an efficient and lightweight manner. Since this was the first year for the team, we had just started, didn't have any resources, we focused on building a simple and functional design. Though this design worked admirably at competition, we in fact took first place in our very first year at competition, it ran into a couple of problems. Primarily, this simplistic approach used to design this vehicle required us to use aluminum honeycomb extensively. While the material is relatively strong, it's very heavy, and our vehicle, in fact, weighed over 70 pounds. In an efficiency competition, weight is perhaps one of the most important characteristics in improving efficiency, and this significantly hurt our results. It also lacked some structural rigidity that we found later on, and after competition, it lacked reliability as well. If you go to our shop at the University of Illinois, you can still see bits and pieces that fell off after we came back from competition. So we took the lessons that we learned from this design and incorporated them into our design for this year's vehicle, the 2013 car. We looked at industry and the carbon fiber monocoque work that was being done by the supercar manufacturers, Ferrari, Lamborghini, Porsche. They all used this new carbon fiber monocoque technology to develop exceedingly lightweight vehicles that are extremely strong as well. However, we didn't have the resources to develop a complete carbon fiber monocoque like Porsche or Lamborghini do. We didn't have millions of dollars to spend on specialized equipment to do that. However, we did find an interesting manufacturing technique called the tab and slot design. Essentially, this allowed us to take one panel of carbon fiber and Nomex honeycomb and cut it into the various pieces we want and put it together like a giant puzzle piece. In doing so, our vehicle was considerably lighter, approximately 26 pounds less, and it was stronger as well. And here you can see how the entire vehicle goes together, like a big puzzle piece. It kept the simplistic manufacturing techniques that we used in the previous vehicle and allowed us to produce the chassis very quickly, but it increased the strength considerably as well. So if the chassis can be thought of as the skeleton of the vehicle, the body is the skin, which holds everything in. In 2011, when we began, we realized that aerodynamics would play a crucial role in designing a vehicle. Therefore, we used this picture at the top, we used this aerodynamic airfoil profile to model our vehicle. Unfortunately, we realized a bit too lately that we couldn't produce this vehicle. Though on paper, on the CAD software that we were using at the time, it made perfect sense and had the aerodynamic characteristics that we were looking for. In the real world, actually producing such a vehicle was far from simple. We simply didn't have the resources available to us to produce that car. And so you can see that our initial design did not translate very well to our final product. Moreover, if you look at the aerodynamic characteristics of our final design, and given the ad hoc nature in which it was produced, it really was not a very aerodynamic vehicle. In fact, with a coefficient of drag of 0.45, it had the aerodynamic characteristics of a truck. Certainly not what you want for an efficiency competition. In fact, we lost almost 243 watts of power to aerodynamic drag alone. Given that our vehicle was outputting about 4 kilowatts of power, this represents almost 6% waste of energy just to air drag alone. So in this year's design, we began by first looking at how are we going to build this car? How can we actually produce what we're going to design in the software and on paper? And as you can see, the final design and the initial design match much better than they did the year before. We also were able to considerably improve the aerodynamic characteristics of this vehicle. With a coefficient of drag of 0.29, this vehicle is comparable to a Toyota Prius, one of the most aerodynamically efficient vehicles on the market currently. Moreover, we significantly reduced the aerodynamic drag, almost a 36% decrease, and only lost 156 watts of power. Finally, we come to the heart of the vehicle, the powertrain itself. From the beginning, we wanted to push the boundaries of what was possible, and we wanted to incorporate novel technologies that weren't really being considered at the university at the time or among the various other design teams. And so we focused our work on fuel cells. This powertrain configuration utilized a fuel cell and 2 wheel hub motors to power the vehicle. While this considerably simplified the powertrain system, we soon realized that it wouldn't allow us to meet our original goals. This vehicle design only allowed us to go approximately 18 miles per hour, not the 30 that we had originally intended for. It proved to be rather unreliable. We found that these motors that we were using were not built very well, and therefore we continuously had efficiency concerns as well as reliability concerns. So for those of you who aren't sure how a fuel cell works, let me walk through the basic principle of a fuel cell. It works very similar to a battery, except fuel is continuously fed in at the anode. In our case, hydrogen. Once it's introduced into the anode, there is a platinum catalyst which allows for the dissociation of the hydrogen atom into protons and electrons. Only the protons are allowed to pass through the semi-permeable membrane to the cathode side. This forces the electrons through an external circuit, creating an electric current, which we then use in our final vehicle. Eventually, the electrons meet up with the protons and oxygen from the air to produce water vapor. So the overall reaction is perfectly clean. The only byproduct is water vapor and heat. Some challenges still remain. The fuel cell that we use in our vehicle, for example, was $25,000 and 6.7 horsepower. So 6.7 horsepower is about what a lawnmower engine is. And I don't know about you, but I wouldn't want a $30,000 lawnmower. But as we increase the or rather reduce the amount of platinum needed in these fuel cells and increase the amount that we're producing, we can take advantage of economies of scale and significantly reduce the cost. A recent Department of Energy study actually showed that if we could produce approximately 200,000 fuel cells, we could reduce the cost to be comparable to internal combustion engines. That still leaves other concerns such as infrastructure and where do we actually get the hydrogen, but it's a step in the right direction. And so actually here I have a small demonstration for you of how a hydrogen fuel cell vehicle works. It's a toy. I know we all love toy cars, at least I did when I was growing up. And when we use these in demonstrations at the university, everybody loves them, whether they're 5 or 50. This vehicle is essentially running on the reaction that I just showed you earlier. It has a reversible fuel cell where if you input current in one direction, it converts water into oxygen and hydrogen. And then when the hydrogen is used in the opposite reaction, it produces an electric current which runs the motor. Given this fuel cell technology, one might ask, what about the entire cycle of extracting hydrogen? This chart here, produced by NREL, shows the wheel-to-well analysis of how efficient using hydrogen actually is. One can see that even in the most unfavorable scenario, hydrogen is about twice as efficient as using oil combustion in an internal combustion vehicle. Our vehicle, our fuel cell, is rated at about 60% efficiency. Comparable internal combustion engine is probably maximum 20% efficient, and diesels may be about 30% efficient. So one can definitely see the benefits of this technology, though considerable amount of improvements still need to be made. And if you look at that fuel cell demonstration, the toy that I had over there, our second year vehicle was very similar to that. The 2013 vehicle used a centralized motor like that vehicle uses in order to increase the power and torque and reach our final speed requirements. While this vehicle just fell short, I think, of reaching about 26 miles per hour, we were able to get considerably closer to the 30 mile per hour requirement and make the vehicle more comfortable in the process. However, we found that using a centralized motor and a chain and a differential introduced too many conversion steps in the mechanical process, which led to significant inefficiencies in the vehicle. So this year's team is looking at a different option and looking at doing a hybrid of the two vehicles. Speaking of this year's team, they're well on their way to producing a final vehicle. They're farther than where we were at this point. This is taken from their drawings, and they have the chassis and body design already completed. They'll soon be analyzing these vehicles, figuring out the rest of the components, but it looks like they're actually making progress and certainly have learned from the mistakes that we made in the past. While I've talked about engineering and the design aspects of this vehicle, I'd now like to talk about another challenge which is just as difficult, and that's the funding aspect. Our vehicle was approximately $57,000. That's how much money we had to collect and spend to build that vehicle, including the $25,000 for the fuel cell. Now, compared to Tesla, which has billions of dollars in funding, $57,000 doesn't seem like a lot, but for a student team, it's a small mountain. We reach out to industry and our sponsors to provide us with that. And so I have to thank all these sponsors who do see the benefit of student-led design in providing that funding and in supporting us not just with money but also with engineering support. And without their support, we wouldn't have been able to develop a vehicle like you see here. So one may ask, why do these companies sponsor student-led design like this? Certainly they have their own projects to worry about and their own in-house work to be done. But I think that they see the benefit in student design competitions as being a way to encourage students to become engineers and designers in the real world. I feel that they see that these kinds of experiences build practical knowledge rather than just classroom knowledge in the students that participate. As a participant in these competitions and now as an advisor for the team, I can state without a doubt that student-led design teaches teamwork, it connects disparate ideas and disciplines, and it reinforces classroom concepts. While the university is great at teaching us the theoretical, oftentimes the practical application of what we're learning is left behind. And it's left to industry and the actual career that students pursue to teach. So to the students that are watching today at the various high schools and universities that this is being distributed to, I encourage you to get involved in design competitions such as these. First of all, they're fun. I can say that I had a blast participating in this. But more than anything else, I think I learned how to take what I've learned in the classroom and apply it in a practical scenario. It allowed me to build upon my knowledge and further my knowledge in a fun and engaging manner, which, as much as the general curriculum attempts to do, can only be done through a hands-on project such as this. And then to industry, who is in the audience today, as well as watching this video on YouTube a few months from now, I encourage them to participate in these competitions and to reach out to their local high schools and local colleges and see how they can help. It doesn't necessarily have to be monetary funding or supplying them with particular equipment, just simply talking to students and seeing how what they're doing, seeing how your expertise can influence the students and what they're doing would make a lot of difference in these student-led design competitions. In conclusion, I feel that student-led design certainly is beneficial for students, and it benefits students by developing outgoing students into outstanding professionals. But more importantly, it engages students into innovating and to finding new ideas and new technologies and making something of them. And I feel that if industry doesn't support these types of endeavors, who knows how many innovators and inventions we may miss out on in the future. Thank you.